let us discuss electric power in CR circuit. The way in which we have calculated power in LR circuit, almost in the same fashion, we just have to consider electric power in a CR circuit also. When we consider CR circuit of AC, we know current leads the EMF by pi by 2 radian. In other words, we can call the same thing that EMF lags behind current by pi by 2 radian. When we just plot the corresponding phasor diagram for that, I can just show you. This is the direction of potential difference across the resistance. Then the potential difference across the capacitance will be downward. What for also we can understand, the moment we take this is the direction of potential difference across the resistance, along the same direction we will be finding the virtual value of electric current. That means this virtual value is leading this VC by 90 degrees. Then automatically VC now should be drawn downward. Now VC and VR both are mutually perpendicular to each other. Then what would be the value of virtual EMF? Virtual value of EMF now can be taken by considering that it is making an angle phi with the direction of VR. Now if you look at this equation, what exactly is the value of cos phi? That is what we want, because power in general is virtual value of EMF into virtual value of current into cos phi, which of course we have called that one as a power factor. Now the question is, what is a power factor in the case of a CR circuit? What is a power factor means? Then we can write the same cos phi from this phasor diagram. Cos phi is equal to VR, that is adjacent value, by hypotenuse over here, that now becomes EV. But we can directly understand VR divided by root over VR square plus VC square we can write. But we can rewrite the same this way in terms of virtual value of current. The same equation can be repeated this way, R by root over R square plus XC square. In fact, we all can understand directly that XC is the value of capacitive reactance. Its value also is known to all of us. It is 1 by omega C. Therefore, I can rewrite the same equation this way, R by root over R square plus 1 by omega square C square, where omega is angular frequency and C is the capacitance that is connected in the circuit, which is taken as a CR circuit here. So when we consider this way, this represents the value of cos phi, which is to be called as a power factor. So considering this value, what is the power now across this CR circuit? Power is equal to virtual volt value of EMF into virtual value of current into this value of power factor. That power factor as such, we have written its value here. I can write the same this way as R by root over R square plus 1 by omega square C square. This is one form of that equation for power in a CR circuit. But we in fact know that virtual value of current can even be written as E by Z. What is that Z? In alternating current circuits, Z represents the value of impedance of that circuit. That impedance, otherwise we can call it as the resistance which has been offered to alternating current by this CR in this particular case. Therefore, we can even rewrite the same equation this way: virtual value of EMF into virtual value of EMF by impedance into the value of power factor, which we have got as R over root over R square plus 1 by omega square C square. This is the way we can replace this IV by EV by Z. But in fact, we all can directly understand Z is equal to, that is impedance of this CR circuit. What is the formula for impedance now? It's R square plus 1 by omega square C square. This is the value of Z. When I substitute this value over here in place of Z, what would be the total power we are going to get? Power is equal to virtual value of EMF square by this value of Z, which now can be written as R square plus 1 by omega square C square whole under root into the value of power factor, which now can be written R by root over R square plus 1 by omega square C square. Since the denominator is same in both the cases, that root goes off when we multiply. So straight away we can write that power is equal to virtual value of EMF square into R divided by R square plus 1 by omega square C square. This is another version for the same electric power in the case of CR circuit. So the same equation we have got in a slightly different way in the case of LR circuit. What is the difference you find in that one and this one? The value of Z that varies. Here in place of 1 by omega square C square, we have to write omega square L square if it is LR circuit as such. So that is the major variation what we have to understand. So for remembering electric power, it is better to remember two formulae. One is this equation: P is equal to virtual value of EMF into virtual value of current into the power factor, which is R by root over R square plus 1 by omega square C square. What is the other version of the same equation now? Electric power P is equal to virtual value of EMF square into R by R square plus 1 by omega square C square. This is the case of electric power in the case of CR circuit as such. Let us consider LCR series circuit of AC. In that circuit also, we have to calculate the power factor to calculate electric power. So the point here is LCR series circuit. LCR series circuit of AC. In LCR series circuit, we can draw this phasor diagram this way. The value of potential difference across the resistance if I take along x-axis. Along the same direction, we will be finding the virtual value of current also. Then if we take the value of VL, that is the potential difference across the inductance coil, that is VL, if I consider upward, because it leads this current by pi by 2 radian. And we can write in the same manner potential difference across the capacitance that lags behind this current again by pi by 2 radian as such. So this is actually the phasor diagram what we can understand from LCR series circuit as such, as far as power calculation that's concerned. Now, if I consider VL is greater than VC, then their resultant will be in the upward direction and its value now will be VL minus VC. Suppose if VC is greater than VL, nothing wrong, that VC minus VL will be downwards now. Only that is the difference. But whatever be the case, the resultant of these two will now be simply the difference of these two values, that is VL and VC. Suppose if VL is greater than VC, their resultant will be in the upward direction this way, that leads this current by pi by 2 radian. Suppose if VC is greater than VL, their resultant will be downwards, and there one can reiterate that the VC minus VL will lag behind this current by pi by 2 radian. So whatever be the case, this is the resultant of these two values. This VR, both are perpendicular to each other. Then we can once again draw the value of virtual EMF. Virtual value of EMF over here now becomes the resultant of these two. That means if I consider this angle, what this virtual value is making with the direction of current, if I consider that one as phi, then this power factor cos phi now can be written this way: adjacent value, that is VR, divided by hypotenuse over here, that is virtual value of EMF. But again we all in fact know this VR divided by root over, what will be the value of virtual EMF here? It is VR square plus VL minus VC whole square, because this is the resultant of these two values, already we have seen that. So we can write VR by root over VR square plus VL minus VC whole square. This is the value what we call it as power factor in the case of LCR series circuit. Let us rewrite the same equation in a different way now. This can be rewritten as R by root over R square plus XL minus XC whole square. In fact, one can understand this XL is called inductive reactance, of which the formula is omega L, and XC is called capacitive reactance, of which the formula is 1 by omega C. Now if I write those two values here, this becomes R by root over R square plus omega L minus 1 by omega C whole square. This is the point one should understand from this equation. Whether omega L is greater than 1 by omega C or 1 by omega C is greater than omega L, this value will not vary. Only thing is the direction of EV that changes, that only varies, but the total magnitude of this power factor will not have any sort of an influence of that. Therefore, naturally the value will remain the same. The magnitude of cos phi, that remains same whether VL is greater than VC or VC is greater than VL, whatever be the case. Now one can write this equation as power factor. Then what would be the power now? Power now becomes virtual value of EMF into virtual value of current into the value of cos phi, which is to be called the power factor. So we can rewrite the same equation this way: P is equal to virtual value of EMF into virtual value of current into the value of R by root over R square plus omega L minus 1 by omega C whole square. This is one form of this equation for power. So that is one way or one version of this electric power across LCR series circuit what we are finding. The same equation can even be rewritten like this. We can understand the virtual value of current IV can be written as EV by Z again. That Z is called again impedance of LCR circuit in this case. Therefore, we can rewrite the same this way, EV into EV by Z into this power factor, that's R by root over R square plus omega L minus 1 by omega C whole square. This is the equation. But we know pretty well the value of Z in this case of LCR series circuit again becomes R square plus omega L minus 1 by omega C whole square, whole under root. Therefore, the value of P, when you substitute that one here, can be rewritten as EV square into R whole divided by R square plus omega L minus 1 by omega C whole square. This is the final version of the same formula for electric power. So, power in LCR series circuit, suppose if we want, either we can calculate using this formula or we can calculate the same using this formula as well. So, as far as electric power is concerned, in LCR circuit, in LR circuit, even in CR circuit, how to calculate the values like we have discussed. Now, the question is, whenever LCR circuit is in resonance, already we have discussed earlier that the total circuit becomes resistive that time, and numerically inductive reactance, that is XL, and capacitive reactance, that is XC, are going to be equal. Not only that, as far as the frequency part of it is concerned, angular frequency of that circuit, LCR circuit I am talking about, that is omega is equal to 1 by root LC we write. That is angular frequency formula. Exactly in the same manner, we have written an equation for linear frequency, that is also called resonating frequency. Small f is equal to 1 by 2 pi under root LC. But now the question is, how this omega varies with the value of current there. Say for example, when we just plot a graph this way, taking the value of omega on x-axis and considering the value of current along y-axis. Now this graph of course indicates at different resistances in the circuit how we get the variation in the current when the circuit is in resonance. So, three things we have to understand. One, the circuit is supposed to be in resonance, and second one, what is the resistance in the circuit that time, and third aspect, how the current that varies with respect to the value of omega depending on the resistance in the circuit as such. Suppose if I take the resistance in the circuit as R1, then what we observe here is, this is the corresponding value of omega where we are finding the current is going to be maximum, and this current when I call it as I naught, this value as omega naught. So, this is the corresponding resonance frequency of that circuit when the resistance in the circuit is R1. Suppose if I reduce the resistance, then we observe that the value of current increases like this. That means the size of this peak is going to be more than the earlier value. If you take R2 is less than R1, the corresponding maximum value of current also increases over here. This is for what value? that is omega naught, which is to be called as a resonating frequency there. So this is the concept. So when we take one more graph like this, suppose if I reduce the resistance in the circuit further, then again I will get another peak of which the size is further larger when comparing to the earlier value. So what we should understand from this type of a graph, as the value of resistance decreases, the current in the circuit automatically increases. That is one area which we have to understand. So what is the relation between these three values here now? R1 should be greater than R2, should be greater than R3. That is, R3 is very less. Suppose if I consider the current over here as I1, here as I2, here as I3, in what way these currents are related now? I can take I1 is less than I2 is less than I3. So these two are the points we have to understand. In fact, the sharpness of this particular circuit or the sharpness of this particular graph I am talking about, I repeat, the sharpness of this graph that indicates that the current is going to be very, very high, and at the same time that directly gives you the resistance at that particular value of current is very low. More the sharpness, more the peak size, it is very clear current is increasing and resistance in the circuit is going to be decreased there. But generally this sharpness and other things we used to measure in terms of Q factor in alternating current circuits. What is this Q factor in general? Q is for quality. So what is Q factor otherwise called? It's called quality factor. That in short form we call it as Q factor. What is the formula for this Q factor? Q factor is nothing other than PD across L or C. That is, L is inductance, C capacitance. Potential difference across L or C divided by the value of applied voltage. The value of applied voltage. That in other words we can write it either VL by VR, or you can write the same as VC by VR. So what we should understand in this particular case is, lesser the value of resistance, correspondingly current increases over there, and we can definitely understand the quality factor over there in that circuit is very high. So generally the quality factor, whenever they ask us to calculate in any of the circuits, better remember this formula: potential difference across inductance or capacitance whole divided by the value of applied voltage. Applied voltage is nothing other than the potential difference existing across the resistance, because whenever the circuit comes into resonance, then the effective resistance in the circuit becomes simply VR itself, because the circuit is going to become resistive circuit that time. That is a point one has to understand. So this is one area we have to remember as far as alternating current circuits that's concerned.